Sir, we are live now. Please start.
Yeah, so just here to see now most of the course is over, all the lectures are up on the website and so on. So we thought we'll have one live session and see what questions you have. Both me and Vishwanath are here today. So you can ask questions on the in the chat. So the syllabus of the course is on the, of course, on the portal itself, though there have been some slight small changes to the syllabus. That is, we did not cover all the topics that were in the syllabus. But if you go to the portal, I'll just show you. So if you go to the portal, the course layout, we have permutation groups, symmetries of graphs, abstract groups, group actions, Silov theorems. So pretty much everything has been covered, except perhaps what we had promised, Jordan, Holder, and Kroll-Schmidt theorems. These will be, and maybe some amount of tensor products. These will be covered in Algebra 2. Vishwanath, I hope I got.
Yeah, that's right.
Yeah. So that's the syllabus. We leave out Jordan, Holder, and Kroll-Schmidt theorem. There's a little bit on tensors. In I have one long lecture on tensors, so that's there. But yeah, besides that, so that's basically the syllabus. There's not much change in that, and the exam will be based entirely on that.
Any other questions on the lecture material and so on? So the exam itself, the assignments are, of course, they are good preparation material in some sense. So if you can somehow solve all the assignment problems and ensure you actually understand the concepts that go into them, that should give you a good preparation for the final exam.
Yeah, definitely. And the exam is quite similar to the assignment in the terms that, it's also multiple choice and objective type. There'll be a few numerical answers, multiple choice questions, and
Maybe I can answer that. So someone, Mohan says, what is the eigenvalue of a matrix? Of course, we didn't quite talk about linear algebra from first principles in this course, we sort of assumed a lot of this. But given our focus on modules and submodules and so on, this whole notion of eigenvalues and eigenvectors can be rephrased in terms of the notion of submodules, for example. So maybe I'll just briefly say something about this. The definition itself goes like this: if you have a matrix A, n cross n matrix, then you say that lambda is an eigenvalue. Lambda is, let's say everything's over the complex numbers, for example, then lambda, a complex number, is an eigenvalue if there exists a non-zero vector. So lambda is said to be an eigenvalue if there exists a non-zero vector x in Cn. So there's a column vector such that A multiplied by x just gives you lambda times x. Okay, so this is the usual definition of an eigenvalue. So for lambda to be an eigenvalue, there must exist an eigenvector with this property. But if you sort of look at the way we thought about vector spaces and linear operators in this course, we sort of took the point of view that if you have a linear operator or a matrix A, then what it does is to make this vector space Cn into a module. Cn becomes a module over the ring C. Let's give this variable a name Ct. Okay, T is just some indeterminate. So Ct is the polynomial ring. And we said you can make this into a module via the following definition. If you have a polynomial in T, so a typical polynomial looks like summation. Let's just write it out in full. It's like a0 plus a1t plus an t power n. And when you make this polynomial act on some vector x in Cn, so the action is defined by saying that, wherever you see this little t, you just replace it by this matrix A. And here where you see t power 0, that is, there is no, there's a constant term, then that's just the identity. So look at this operator, matrix an capital A power n, and then you make it act on the vector x. So what does all this have to do with eigenvalues and eigenvectors? Well, if you have an eigenvalue and an eigenvector, so you have an eigenpair, then that one-dimensional space spanned by x. So from the point of view of our course, here's what an eigenpair is. So lambda x is an eigenpair, by which I mean this implies, at least, so here's a one-way implication. This means that the span of this vector x is invariant under the action of A, or in other words, this is a submodule. So the span of x is a one-dimensional space. This is actually a submodule over this ring Ct. So that's sort of one way of thinking about what what an eigenvector is. At least it's a one-dimensional Ct submodule of Cn.
So it's the other way around, right? Every one-dimensional submodule of Cn is also spanned by an eigenvector, and the eigenvalue is the constant by which lambda t acts, t dot t.
By which t acts, yeah, absolutely. So you can sort of also make this into a converse statement. If I have a one-dimensional space which is a submodule, then any vector, any basis vector of that space is actually an eigenvector. And to figure out the constant lambda, I mean the eigenvalue lambda, you just have to see what is the action of t on that vector. So t acts on x must be some multiple of x because it's a one-dimensional space. That multiple is exactly the eigenvalue. So this is just a sort of a more maybe sophisticated point of view, but that's the point of view we have taken in this course. Yeah. Any other questions?
Shall I take that or?
Yeah, sure.
Okay, so yeah, so maybe
Yeah, I'll just stop share. Yes.
yeah. So the thing is, if you have two matrices, when can you multiply them? So if A is an m by n matrix and B is a k by L matrix, then you can only do AB only if n is equal to k, right? So you cannot multiply two matrices unless the number of columns in the first matrix is equal to the number of rows in the second matrix. So if you want to form a ring, so matrices, only square matrices form a ring. So if to get a ring of matrices of a fixed size, so m cross n over subfield k is a ring only if and only if n is equal to m, because you will not be able to multiply an m by n matrix by another m by n matrix unless m is equal to n. So this is one reason why we often think of matrices, of square matrices, when we want to talk about a ring. But you can talk about m by n matrices as a module over, so m by n k is in m by m k module, that is given a matrix X in here and a matrix A in here, you can talk about A dot X, which is in m by k. Okay, but because rectangular matrices don't form a ring, there are a lot of things we cannot do. We cannot look at the rectangular matrices as a ring. And also when we talk about rational canonical form and Jordan canonical form, it doesn't make sense to change, to do x a x inverse. You wouldn't be able to write x a x inverse unless both m and n were the same. But we did look at rectangular matrices when we talked about equivalence of matrices, where we somehow decoupled the left multiplication and the right multiplication. So we had two notions of, I think we said that A is similar to B means that B is x a x inverse. For this, you need A to be square matrix. But then we also had equivalence. A is equivalent to B. This is true if and only if B is equal to X, A, Y for some invertible matrices, X and Y. So here, these things could be M by N matrices. And in that case, this would be an M by M matrix and Y would be an N by N matrix. And in this case, because there's X and Y are somehow not related, this relation becomes, it's much easier. There are far fewer classes, and over a field, these are completely determined by the rank of A and B. Over polynomial rings, this is only determined by the um, Smith normal form. I know Vishwanath has something to add to this.
Yeah. So also when one talks about see, homomorphisms between free modules and so on. So if you have, or let's even say the simplest cases of case of vector spaces over a field, if you have a homomorphism from, I mean, a rectangular matrix is just a linear transformation from, say, some Cm to a different Cn. And part of the reason, just to sort of reiterate what Amri said, is why these rectangular matrices don't seem to be as important is that, I mean, they don't have a ring structure. You don't have a nice way of composing linear transformations which go between two different spaces. So only when the map is between the same space. So this is what we call endomorphisms versus just ordinary homomorphisms, which would be between two different spaces. Yeah. So I mean, just say these did occur in the course, rectangular matrices in various places. The key reason why the square matrices seem more important is that they form a ring. Maybe I can just address one of the questions which was posed on the discussion group as well, sort of an addendum to the notion of direct sums of modules. In the course itself, we own okay, is my screen visible? Okay. So in the course itself, we talked about this notion of direct sums for modules, and we were usually only dealing with a finite number of them. So if I have M1, M2, Mk, which are all modules, then we said the direct sum is just all, well, as a set, it's just the Cartesian product itself. Just take x1, x2, xk, xi is coming from the corresponding modules in mind. So all the modules here are modules of the same ring R. They're all R modules. And this is just defined with respect to component wise. The operations are you add component wise, you sort of scalar multiply component wise. And this was the notion of a direct sum. And someone asked on the group how this generalizes if you have an infinite collection of modules. So the usual way in which one writes is, so suppose I have a family of modules, I ranging over some indexing set I. In other words, this set could be finite, infinite, whatever cardinality, uncountable, and so on. You have some collection, possibly an infinite collection. Then one wants to have a notion of a direct sum, sort of analogous to what we have before. Now, the point is, there are actually two possible definitions here. One, you could just see what we did in the finite case and say, well, as a set, let's start with the collection of all tuples. In other words, I just take the Cartesian products of these modules, xi coming from mi. So this is sort of like the full Cartesian product, if you wish. So I just put a cross there. As a set, it's all ordered tuples, or you can think of it as functions from I to the union of the mi's and so on. But so anyway, I mean, we understand what this means. But here you define the operations again component-wise with component-wise operations. So maybe, I mean, let's make this slightly simpler. So let me just deal with an infinite collection indexed by the natural numbers. So suppose I say I have M1, M2, M3, M4, and so on, and I want to understand what this infinite direct sum means. Like I said, there are two possible ways of thinking about it. Number one, you could just say take all sequences I greater than or equal to 1, where xi comes from mi for all I. Take this set and just perform operations component wise. So that would be one way of doing it, and that produces well, that is a module in fact, but we call this the direct product rather than the direct sum in this case. So this is the direct product of these modules. In the situation where we only have finitely many modules, the direct sum and the direct product are the same notion; they coincide. When you have infinitely many of them, this particular version is called the direct product, and the direct sum itself is, well, it's a subset of this. So what is the direct sum mi? You take sequences, but you don't allow the infinitely many, I mean all but finitely many of the terms must be 0. So you force this property that xi is 0 for all large I, for all I greater than or equal to n for some n. So there exists n, some natural number such that all xi's beyond that point are 0. Okay, this is sometimes called the set of finitely non-zero sequences. And this collection again, so it's still component-wise operations. It's actually a submodule of this large module, and this is what's called the direct sum in this case. Okay, and so one can check that this is a module. It's closed under addition and scalar multiplication and so on. And so there is some subtle reason why one wants to do this. So in some sense, a direct sum or a direct product is defined by the property that we wanted to have. So the direct sum, for example, if you recall in the finite case, for a finite collection of modules, we said the following: suppose I have finitely many modules M1, M2, Mn, and suppose from each of them I give you a homomorphism to another module. So I have homomorphisms Fi from Mi to N. So these are all R module homomorphisms. Given such a collection of modules and homomorphisms to a single target module N, then what it gives you is it defines then there exists a unique R module homomorphism, let's call it F, from the direct sum Mi to N. And how do you define this? So this is again an R module homomorphism, such that with the following property, that if you think of Mi as being a subset of this collection, so remember each Mi itself sits inside this direct sum in the, as you know, the sequences which are 0 everywhere except in the ith component, then this F on such sequences, so let's write it like that. If we take sequences which are 0 everywhere except in the ith position, then this F is just the same as Fi. Okay, so this is just another way of saying that F composition, these inclusion maps will give you the original Fs. So I mean, we talked about this in the course, and a module which satisfies this property is what we usually call a direct sum. Okay, and in the infinite case, you can check that this particular version that we talked about, this the second guy, that's the one which has that property. Okay, the first one will not have that property. And the first one has a different property, which is that if you have projection maps and so on, then you have this. So anyway, I mentioned this partly to advertise some of these notions in Algebra 2, where these are all part of some more abstract framework of category theory and so on. And that's something which will come up, be a big part of Algebra 2.
Where do mechanical engineers apply algebra?
Like, as linear algebra certainly plays a very big part. I mean, your original question about eigenvalues, for example, I guess those are certainly very important. But I suppose even group theory at some level is probably applying.
Yeah, I don't actually know enough about where what exactly mechanical engineers need, but all engineers need also certain optimization techniques. You need linear programming problems, and these are all very strongly based on linear algebra, but not so much as far as I know on rings and modules and abstract theory. However, there's a very interesting connection between linear programming and rings, in fact, uh, particularly what is known as integer programming. So if you want to count lattice points inside polytopes, then these are closely related to algebra and ring theory, and there are lots of very interesting theorems that address these questions. But I'm not sure if these come up much in mechanical engineering. They definitely seem to be more in computer science and algorithms and things like that. Um, it's It's a nice question there. Yeah.
Is the infinite direct sum?
Direct
Summand
summand
of.
of the, yeah. It's a very interesting question.
I suppose not. Um, how do we see this?
Well, if you just look at vector spaces, for example, isn't it in that case?
So you want to find a complementary submodule whose okay, to the infinite direct sum.
I guess if you just take, for example, the ring to be a field, let's just take the field of complex numbers, and you take, infinite direct sum C, the complex numbers itself over all integers as a, so that's an infinite dimensional subspace of the product where all coordinates are allowed to be non-zero. My feeling is that you can actually find a complement to that, right?
In that,
Because well,
no, I mean there it is just vector spaces anyway, right?
yeah. So there it's definitely, but then maybe something similar can be done in the.
Arbitrary modules from arbitrary collection.
Yeah. But see, how would we do it there, right? So we would just look for a basis. So what we would do is we would take the quotient of the infinite product by the infinite sum. We would find a basis for that vector space, which we cannot really write down in I don't know of a nice way to write down such a basis, but it exists using abstract set theory and so on. And then we would pull it back via the quotient map to set of vectors in the infinite. Maybe I should write something here. So this very, very interesting question. So let's take this picture here. So we have direct sum I equals 1 to infinity of, let's just say C inside direct product. This is a subspace of the direct product I equals 1 to infinity of C. So the only difference is that these are vectors A1, A2, A3, where AI is equal to 0 for sufficiently large I. And here we would have all A1, A2, right? So this would have all the vectors, infinite vectors, and this would have vectors which are 0. And now this is a vector space over the complex number. This is another vector space of the complex number. So for brevity, let me just call this V, and let's call this V bar. And so you can form the quotient space V bar mod V. Let's call that W. And then you take a basis Wi. I belongs to some indexing set I don't know what this set is. It's not going to be countable, of W, and then take W tilde I in V bar, whose image is, so you have this quotient map Q from V bar to W, and so take W tilde I belong to V bar such that Q of W tilde I is Wi. And then this space will be the span of this will be a complement of I think this will be a complement of V in V bar. So maybe this kind of idea can be used to construct in general a complement perhaps. So the question is the quotient a free module? If the quotient is a free module, then we could do the same thing, I guess. And I would expect the quotient to be a free module. But
No, but this is of arbitrary modules, right? I suppose the question is have
oh
an
yeah,
arbitrary collection
module.
of.
Correct. Yeah. Yeah, this could be more subtle then.
The generality.
Maybe one could look for interesting examples even in integer abelian groups, right? So what if you take Z mod 2 plus Z mod 3 plus Z mod 4 inside Z mod 2 cross Z mod 3 cross Z mod 4?
I mean, the naive thing of trying to take all sequences which are necessarily infinite, which never vanish, sort of the complement. That kind of thing, of course, that's not going
That's
to
not
work.
a submodule, right?
Not even a submodule. Yeah. Take infinitely many copies of Z.
I was thinking, what about, you know, something like Z mod 2 cross Z mod 3 cross Z mod 4 containing Z mod 2 plus Z mod 3 plus Z mod 4 direct sum. What would a complement of that look like? It's not at all clear to me. Because now any, oh, that would be a torsion free module, I guess. There it might actually work. The quotient would be torsion. But yeah, if you take infinite direct sum of same copies, also, okay, that's a good question. Z as Z module, yeah. Infinite direct sum. So then that quotient would be a free module, I guess. And so you could probably do what I argued here, right? Because it's torsion free, and so it should be a free module. So what I'm saying is that exactly this is what I've done here, but instead of C, you just take Z. And all you need to know is that this is a free module. V bar mod V is free. Is that clear that V bar mod V is free? So certainly if some, it's a torsion free module. So maybe I think, yeah, so it should be free. And so you can just do the same argument. Yes. Only not 100% sure that this quotient is going to be free. Because it's not finitely generated, but maybe that's still true.
Yeah, I guess good question, but seems slightly more subtle.
So it only comes down to this, whether V bar mod V is free in this case.
Right. At least in this case. Yeah.
Yeah, and I think it should be. I just can't think of a proof right away. But yeah. Yeah, it's a very nice question.
Yeah.
One has to be careful with infinite abelian groups. I mean, all kinds of crazy things happen.
Yeah. Any further questions?
So if that quotient is not free, then we wouldn't be able to do it, right? I mean,
I guess projective is another.
yeah, okay. Okay, but yeah. Yeah, we'll also think about it.
Any other comments or questions? Okay, so maybe should we call it a day then?
Yeah, I guess. If there are no more questions, we can probably stop.
Yeah, maybe.
Thanks.
Thanks, thanks to those who came to the session, and good luck for the exams. Those of you who are taking it. So, hope to see some of you at least in algebra.